draw again our perceptron with two inputs, x1 and x2. Inside here, we do w dot x plus b. Then here we have the output through the activation function, w dot x plus b. And we want to model the OR gate. So the OR gate, it has two inputs, x1 and x2, and the correspondent output or label, we will have four options, is right? We can have the pair +1 and +1, which is true. +1 -1, which is also true. -1 and +1, which is also true. And false and false is equal to false. Okay? So this we call the label. And this is basically now the input data. So what happened? I mean, we have a pair. The data is given by a pair, by a vector x, xn tilde, and a label wn for n equal 1, 2, 3, and 4. And indeed, what are these pairs? So we have x1 equal 1, 1, and y1 equal 1, x2 equal 1 minus 1, and the label is equal to 1, x3 vector equal to this, equal to 1, and x4 equal to false. Okay, these are the data available. Okay, and so our goal is to basically given this data set, given the data and its labels, the associated labels for n equal 1 to 4, find the perceptron parameter w and b such that the output of the perceptron is equal to the labels in the data for all the available data points. Okay? So that's what we want to solve. So we want to find what are the parameters which so that the output of the perceptron is equal to the label data. And of course, what does it mean, this equation here? If we do it more properly, we want to say find w comma b such that yn equal to the label. Remember, these are the data points that we have. But what is the output here? The output here we can compute it with the perceptron formula. So this basically means the sign of W dotted with the data input plus B has to be equal to, has to match the label, data label, for all n, for all the available data. Okay? So we have, we need to find the parameters of the perceptron that satisfy these conditions. And is also, and that's basically, you know, the what is called supervised learning. Because we are we have the knowledge of the labels that allow us, you know, to supervise the learning of this of the perceptron parameters. And this is also this process here of finding the best weights which match the data is also called the perceptron training. So that basically, you know, we can model the OR gate, you know, with a perceptron. And how to, but before going to the details of this, this is basically we will transform it into an optimization problem. Optimization problem. But before doing that, let's try to give a geometric interpretation of all these equations here, which, you know, we can get some visual, if we can visualize what this equation mean, I mean, that's very powerful. And to do that, you know, remember that this is our perceptron. So let's plot. Let's work on the input space, which is given by this plane here. And let's see what are the input vectors, okay? Which are all these pairs, 4 pairs of points. So what happens is that, you know, we can only have -1 and +1, 1 and -1. And so what happened is that the first input data, it is 1 and 1, which is basically this circle here, and correspond to a +1 label, which is basically +1 label means true. And so we are going to color them with these colors here. So these basically correspond to true results. Instead, you know, the empty circle will be a false outcome. So we are done with this. So then we have a +1 and -1. +1 and -1 is down here. And this is also true. as an output. Then we have -1 and 1 here. And this is also true. And then we have, oh, no, sorry, -1 and 1 is this. And -1 and -1, it is this. And I'm gonna do it in red, actually. So the red, basically, it is false. Just to fix the... So you see that here we have the false, true, true, and true. So now, if you observe carefully, we can find a decision boundary which separates the true results from the false outputs. These are the region of true of inputs that are going to give me a true output, and this is the region of inputs that they're going to give me a false outcome. Okay, and so you see that there is more than one line that satisfies this problem, and but it's possible to this line is basically w dot x plus b equals 0, and geometrically, I can basically choose find the slope and the bias such that I can find the parameters knowing the geometry of this line. So basically, this problem, the OR gate, can be modeled with a perceptron, and the solution is geometric. That's what does it mean. Another important thing to realize here that we need to estimate W and B, which correspond to 3 parameters, W1, W2, and B. However, when we draw this line, a line, it is made of 2 parameters, an intercept and a slope. Because we have seen that we can write x2 as minus W1 over minus B over W2 minus W1 over W2, which multiply x1. So in actually, from this geometry, when I draw this line, I can only measure this distance, and then I can also measure this angle here, alpha. And the best that we can say is that let's call this distance L, and we have L equal minus B over W2, and tangent of alpha is equal to the slope minus W1 over W2. So I only have 2 equations for 3 unknowns. The truth of the matter that actually these weights, if we look carefully, the output y is equal to the sine of W1 x1 plus W2 x2 plus B. The output depends only on the sign of this quantity here. And so the magnitude of W1 and W2 is not important. We can rescale W and the results of this operation are going to be still the same. So what is done in practice is it is assumed that the length of this vector is equal to the number of inputs. N is the number of inputs. In our case, means that W1 square plus W2 square is equal to 2 for the problem at tens. Okay? And so, no, this is basically the extra equation that we can use to complete the solution of the parameters B, BW, and W1 and W2. Okay? So, and the reason for this particular scaling will be clear later on when we're going to study the Hopfield network. And usually it is done in such a way that the energy associated to the network is basically linearly proportional to the number of inputs. Okay, and that's why we do this scaling. So this is basically the geometric interpretation. But now let's understand how we can solve this problem using an algorithm. Okay, so and that's the next step. So again, I'm gonna draw again our perceptron. We have two inputs. W dot x plus b. Then here, through the axon, there is the activation function, which is gonna give me the output W dot x plus b. And so remember that what does it mean this quantity here? This output is going to be equal to +1 if this argument is greater than 0. It's going to be equal to -1 if the same argument is going to be less than 0. Okay? Because that's what the sign function does. So we have our data set, which has an input data, input vector, and an associated label, which is a scalar. And we have 4 of these data. So we want to find W and X, W and the weight and the bias, such that we classify correctly each data set at so what does it mean? That we need to make sure that WYN, which is the output of the perceptron for a given data input, this is basically the predicted output for the input xn that we know. We want that yn has to be equal to the label, the data label, okay? And this has to be true for all 4 data sets. And what does it mean, this, what does it mean, this quantity here? This means that the sign of W dotted xn plus b has to be equal to the data label for a given data set, but has to be true for all four. And let's observe, remember that, this label can be just be +1 and -1. If the label that we have from the data is equal to +1, in order to satisfy this equality, we need to have that the argument inside has to be greater than 0. And then this will be satisfied. If it's -1, we want this product, this operation here, argument, to be less than 0. So you can see that in either cases, if I do the product, the data label multiplied W dotted xn plus b is going to be greater than 0 in both cases. You see, when it's +1, this is positive. So basically, when I multiply this number times +1, I'm going to get a positive quantity. If this is negative, this also be negative. When I multiply these two quantities, I'm going to get a positive quantity. So if this condition is satisfied, the data is classified correctly. So data pair is classified correctly if the data pair what? X and Y label. If this condition is satisfied. So actually now we can define a loss function or an energy based on this concept. In particular, we can say I can define the energy equal to minus the data label yn, which multiply W dotted xn plus b. And of course, we can gonna do the sum over all the 4 data points. This energy or loss function measures if we classify the data xn, yn correctly. Why? Indeed, we want E to be the smallest possible. Why? If I misclassify a data point, a data pair, imagine what does it mean when I misclassify the data pair? For what you see before, it means that this product will be negative because I'm not going to match the data. It means that this implies that this product will be negative. And this what imply that this energy, then the energy increases. Okay? Then the energy increases because now this is negative, become plus. And so we don't want that. And so what happened that you see that now we can design an algorithm, optimization algorithm such that it's going to help us to find W and B that minimize the energy E. Okay? Which is given by minus the sum over all data points of the label multiplied by this argument here. So you see that the energy depend upon W and B. And if we want to minimize it, so we will have to take the derivative of the energy with respect to the vector W and the derivative of the energy with respect to B. And so it's easy to see that this derivative, the derivative with respect to a vector is also going to be a vector. If you look here at this expression, we have yn times w dotted with xn. It is clear that this derivative is equal to minus yn label multiplied by xn, the xn input data, and the derivative with respect to the bias, which is a scalar function, a scalar variable, is minus yn hat multiplied by b. It's going to be minus yn hat. So you can see that the derivatives are easy to compute, and having this, once we have this derivative, that as you can see, they depend upon the data points and the labels, we can design the training algorithm, because based on this gradient, based on these gradients, these derivatives, we can design a gradient descent algorithm so that we can iterate over the weights. And the way to design this algorithm is if data xn, yn are misclassified. What does it mean? It means that this product is negative. It will increase the energy. This means yn data w dot xn plus b less than 0 if um, then updates parameters following the following rule. So, you know, the gradient rule. So we say that W at the iteration t plus 1 is equal to the weight vectors at previous time step minus gamma multiply the gradient with respect to the parameter. And then b at t plus 1 is equal to b at the previous time step minus gamma dE with respect to the bias. And you know, the parameter gamma, it is called the learning rate, and it is an hyperparameter of the training algorithm that, you know, can be chosen by the operator. That's why it's called hyperparameter. So we have the freedom to choose it, you know, in order to speed up the calculations. And so you can see that based on this these gradients that we already computed. So the training algorithm is W t plus 1 equal W at time t. So you see that oops. So this is minus yn xn. So with the minus in front, we become plus yn hat xn, and the biased is going to be the derivative is minus yn. So here we have plus yn. So when you can see that the algorithm is, this is the training algorithm, is very easy to implement. And again, you know, this is when a data point is misclassified. I'm gonna write again here the condition. If this is less than 0, then updates parameters, okay? And then you keep going, and eventually, you know, this algorithm will reach convergence, minimizing the energy E, which in our case is equal to the sum from n equal 1 to 4 of yn at w dotted xn at plus b. And that's how, you know, we find the weights of this of the perceptron. And I'm going to show you now a Python code that does that. But before doing that, let's switch now to the Python code. so that we can, I'm going to share the screen now. And actually the video.